Okay, this is part one of the lectures on Doppler shift or the Doppler effect. This is the Doppler effect associated with sound, not associated with light. Okay, there are two physical types of Doppler shifts or Doppler effects. I'm going to demonstrate one of them for you here. What I'm going to do is take this tuning fork, which has a fundamental frequency of 480 hertz. I'm going to give it a whack, and then I'm going to twirl it above my head here by means of this string. Okay, when the tuning fork is moving towards you like so, then the wavelength of the sound waves that are emitted by the tuning fork are physically compressed a little bit. This then means that you're going to hear a greater frequency, that is a higher pitched sound. Okay, the second scenario is what happens if the tuning fork is moving away from you like so. This then means that the wavelength of the sound waves that it emits towards you are stretched out a little bit, therefore you're going to hear a lower pitched sound. This is the first physical type of Doppler shift where you have the physical wavelength of the sound wave changed. Okay, the second scenario, however, is what happens if you have a stationary source of sound and then a moving observer. Imagine that the observer is running towards the tuning fork or running away from the tuning fork. If that's the case, then the situation is actually a Galilean relativity situation. The reason for that is because if you run towards the source of sound, you would measure the speed of sound as greater than 343 meters per second. Therefore, you're going to hear a higher pitched sound. If you run away from the tuning fork, then you would measure the speed of sound as something less than 343 meters per second. Therefore, you're going to hear a lower pitched sound. There are two physically distinct types of Doppler shifts. One where the wavelength actually physically changes, either compressed or stretched out a little bit. And then what happens, secondly, if you have a moving observer with a Galilean relativity situation. Okay, let me demonstrate this first physical type of Doppler shift for you, however, by doing this. Like so. So when the fork is moving towards you, you hear a higher pitched sound. When it's moving away from you, you hear a lower pitched sound. Okay? All right, let me go ahead and set up this first physical situation. Okay, so for this first physical situation here, and we're going to break it up into two parts, we're going to have a moving source of sound and a stationary observer. Okay, before we begin, however, there are some definitions, some terms to briefly run through. So off to the side. First of all is the frequency F. This is the frequency that's actually emitted by the tuning fork itself. That's 480 hertz in my simple demonstration. Okay, and then we have the speed of sound V, 343 meters per second. Okay, and then we have the speed of the source. This is labeled as V sub S. So this is not the speed of sound, this is the speed of the source. Okay, and then we have the Doppler shifted frequency, what it is that we're trying to determine. This is referred to as F prime. This is what's actually heard. Okay, and then a little bit later on, then we're also going to have the speed of the observer. That's referred to as VO. All right, now before I go any further here in this derivation, what I want you to do at this point is pause this lecture and then take a look at the two screencasts or the screencast animations that I have posted for you in today's folder. I've also posted the links that I'm using in that screencast. So go ahead and take a look at that screencast now, please. Okay, now that you've done so, now you can understand the following diagram that I'm about to draw. Okay, let's refer to this scenario here as part A. In this case, we'll have the source moves towards the observer. Okay, so let's say that right here is the source, right here is the observer. Okay, and then the source goes beep, and a sound wave then propagates outwards from that point like so towards the observer. Okay, now let's say that the source is not moving. So then therefore, the next time that it goes beep, a sound wave would propagate outwards from this point, like so, towards the observer to the right-hand side. What that means is that on this diagram, this distance right here is the uncompressed wavelength. This is referred to as lambda. However, the source is moving. So then therefore, the next time that it goes beep, the source is not here. Instead, it's right here. And then the sound wave propagates outwards from that point towards the observer. This then, therefore, right here is the compressed wavelength called lambda prime that you see in the animation in the screencast. Once again, take a look at that animation. And then the last distance on this diagram is this distance right here. This is the distance that the source moves in between beeps. This right here is equal to the speed of the source multiplied by the time between beeps, which is just the period of the sound wave that's actually emitted by the tuning fork. And now we just add things together. Notice that lambda is equal to lambda prime plus VST. And now I just manipulate some of the terms here in this expression to write them in terms of these quantities here. Here's how we do that. Recall that wavelength is speed over frequency. So then therefore the uncompressed wavelength is the speed of sound divided by the frequency that's actually emitted by the tuning fork. Lambda prime, the compressed wavelength, is the speed of sound divided by what we want, the Doppler shifted frequency. And then lastly here in the last term, let's replace the period with just the reciprocal of the frequency that's actually emitted. And now what we do is we just take this expression and solve it for f prime. I'll spare you the algebra. When you solve for f prime, you get this expression here. Like so. Notice how the expression works. The number in the parentheses is a number that is greater than 1. So then therefore the Doppler shifted frequency that's heard by the observer is greater than the frequency that's actually emitted. Also notice that the expression doesn't work if the speed of the source is equal to or greater than the speed of sound. If the speed of the source is equal to the speed of sound, then you end up with 0 in the expression and the expression is undefined. If the speed of the source is greater than the speed of sound, then you end up with a negative number here in the parentheses, which has no meaning in this context. So then, this then means, therefore, that something else has to happen if the speed of the source is greater than the speed of sound. We'll get to that a little bit later on. For now, this only works if the speed of the source is less than the speed of sound. Okay, now let's do part B of this scenario, which is what happens if the source moves away from the observer. When I draw out this scenario, I'm going to end up with an expression that very much looks like this, except a couple of the terms are going to be backwards. Here's then what occurs. Okay, so I'm going to call this B. So now the source moves away from the observer. And then once again, we look at beeps, if you will, of sound waves. So let's say that the observer is here again. Here's the source, and the source goes beep, and a sound wave propagates towards the observer like so. And then let's say once again that the source doesn't move. So if it doesn't move, the next time that it goes beep, a sound wave propagates outwards from that point. This right here is the unstretched out wavelength lambda. However, as you see in the animation in the screencast, the source is moving. So the next time that it goes beep, the source is not here, it's over here somewhere, like so. And then therefore a sound wave propagates outwards from that point towards the observer. This right here is the stretched out wavelength that you see in the animation. This right here is lambda prime. And then lastly on this diagram is this distance right here, the distance that the source moves in between beeps. This is equal to the speed of the source multiplied by the time between beeps, which is once again just the period of the sound wave that's emitted. And now we add things together. Notice that lambda prime is equal to lambda plus VST. Okay, and then the expression, we now replace the following. The stretched out wavelength is the speed of sound divided by the Doppler shifted frequency. The unstretched out wavelength is the speed of sound divided by the frequency that's actually emitted. And then in the last term, we replace the period here with the reciprocal of the frequency that's actually emitted. And then you take this expression here and you solve it for f prime. I'll spare you the algebra once again. When you do solve for f prime, you end up with this expression here. Like so. Notice that the number in parentheses is a number that is less than 1. Therefore, the Doppler shifted frequency that is heard is lower pitched than the frequency that's actually emitted. The two equations there are actually combined into one expression. That one expression is written in the following way. Like so. And there's an easy way to remember what the symbols mean in the denominator of the expression. The top symbol, the negative sign, means that the source moves towards the observer. T for top, T for towards. The bottom symbol, however, the positive sign, that means that the source moves away from the observer. But once again, the easiest way to remember it is that T stands for top, T stands for towards. Okay, this is once again the first physical type of Doppler shift. Now let's take a look at the second. Okay, so for the second physical Doppler shift, now we have a stationary source and a moving observer. So then therefore that person would be a moving reference frame and would measure the speed of sound as either greater or less than 343 meters per second. So it's a Galilean relativity situation. Here's then how we set that up. Okay, right here is the source. Here's the observer, and then for this portion of the derivation, we'll say that the observer moves towards. So then therefore the VO is going to be in this direction like so. Now I know it's been a while since we've seen it. You're going to see it, by the way, a lot more later on in the semester. But right here is the Galilean transformation expression. V equals V prime plus U. And then here are the different reference frames and the object. The stationary reference frame, as it always is once again the surface of the Earth. The moving reference frame, O prime if you will, that's the observer. And then the object in all of this is the sound wave. And now here's how you write the expression for this situation. V, that's the velocity of the sound with respect to the ground. That's just V equals 343 meters per second. This right here is what we want, the speed of the sound according to the observer. And then this right here is the velocity of O prime, the moving reference frame, with respect to O, the stationary reference frame. That's VO. This points, however, to the left-hand side of my diagram, hence a negative sign like so. And now in this term right here, we now replace this term with the following. This is equal to the wavelength of the sound wave multiplied by what we're interested in finding, the Doppler shifted frequency. There's one more step here, however, before we solve for f prime, and that's to get rid of the original wavelength lambda. The original wavelength lambda is the speed of sound divided by the frequency that's actually emitted by the fork. And now what you do is you then solve for f prime. Once again, I'll spare you the algebra. When you solve for f prime, you end up with this expression here. Like so. Notice how the expression works. Notice that the parentheses is a number that is greater than 1. Therefore, the Doppler shifted frequency f prime is greater than the frequency f. Okay, and then the last scenario is just to take the observer and move them in the opposite direction. So then therefore all the negative signs here just become positive signs when we do it. Okay, let me draw it out, however. So now we'll say here for this last part B that the observer moves away. So it's once again the exact same setup, however. The VO points to the right-hand side of the diagram. Therefore, these guys here all turn into positive signs. Once again, we then just solve for f prime. I'll spare you the algebra. When you solve for f prime, you get this here. Like so. And notice how the number in the parentheses works. It's a number that is less than 1. Therefore, the Doppler shifted frequency f prime is less than the frequency that's actually emitted. So you would hear a lower pitched sound. Like we did for these expressions here, we actually combine these expressions here together as well. Let me do so in the following way. And then here's how you read the symbols. It's done exactly the same way with the first set of expressions. The top symbol means towards. So if the observer moves towards the source, then it's the top symbol in the numerator, which is the positive sign. So all that you have to remember is that top means towards. Lastly, the two expressions that you see there are actually combined together into one expression. And this one expression then takes care of every possibility for these one-dimensional scenarios that we're looking at. Incidentally, by the way, all that we are looking at here are one-dimensional scenarios. What happens off to the side and so on and so forth has to do with a little bit of trigonometry. It's not important here for our purposes, however. Okay, so the last step here is now to combine the expressions together. Okay, so here's how we combine the expressions together into one equation which takes care of all possibilities. Basically, let's ask and answer the following question. What happens if both the source and the observer are moving? Okay, to answer this question, let's break this up into a two-step process. First, let's say that we have a stationary observer and a moving source. So then therefore the observer would hear the first set of expressions. Like so. Okay, but now let's say in the second step that the observer starts moving. So what then happens? This gets Doppler shifted. This frequency here replaces this in this expression to then give us the overall frequency that is heard. So now take this original Doppler shift and plug it into here. When you do, you end up with this. This gets Doppler shifted. So now take the bottom set of expressions on the right-hand board and replace the F here with that. Like so. And notice that the value of V cancels out here and here, like so. And now you end up here with one expression that takes care of every possibility. This expression here. Using this expression is easy. All that you have to do is get the symbols correct, and all that you have to remember is that T stands for top, T stands for towards. And then in various situations, you just look at the directions associated with the objects, the source, and the observer. You'll see this in my examples in part 2. I'm not going to record part 2 today, however. I'm going to save that for a later time. So I'm going to go ahead and conclude today's lecture with this derivation. Today's shirt is Abysmal Dawn. Everybody stay safe.